Hi, this week one of our goal is to learn about telescopes. So before we learning about telescopes, we need to know the waves that it's using to create images, right? So let's learn about waves, electromagnetic wave, then reflection, refraction, and let's understand what is a light year is. Well, so you know what are the waves are, right? So all of these are examples of waves. So you may have seen a waves on a rope, and also when you are in beach, you might have seen waves, right? Water waves, and also there are waves on the sand as well. So examples of waves, I would say sound waves, radio waves, earthquake waves, traffic waves, light waves. So light also behave as a wave. All right, so let's understand the qualities of waves. So when we explain about a wave, we always tell someone the wave's wavelength and also pitch, right? So let's see what, and also frequency. So there are three things that you will be using: the wavelength, frequency, and the amplitude. Well, what is a wavelength? So the wavelength is the distance between successive light points on a. So light points might be peaks, valleys, and any point that lightly behaving, right? So here, if you look at this wave, we see a peak there and also a peak here and a peak here, right? So if you measure the distance from peak to peak in one oscillation, so I'm catching one peak over here and I wait until the next peak appear and I measure the distance from peak to peak. So that's called the wavelength of the wave. Then the amplitude. Amplitude is the how high is the wave is from the center, right? So if you draw a center line between the peak and the valley, like the dash line over here, and the height from that dash line to the peak is the amplitude. Also, you can measure the height from the center to the valley. That's the amplitude as well. So we are thinking about a perfect world, like there's no dispersion, so this amplitude is not decaying. But in real life, due to the frictional forces, this wave will decay, so the amplitude will be getting smaller and smaller over the time. But just for the understanding easy, we'll use the perfect wave, like you have the amplitude, continuous amplitude and the continuous wavelength throughout the time. Well, so these pictures are comparing the wavelength and the amplitude. So when we have lower amplitude, it's implies the smaller height or the depth of the wave, and shorter wavelength implies more complete wave fit in a given distance. So given distance, you should find a high number of waves if it has a lower wavelength. Let's analyze it using this way pictures. So as you see here, this one, let's say this is the original wave, and we're going to compare the other waves with the original one. So here, if you see the peak to peak distance on the first one, it's from here to there, but here peak to peak distance is here, right? So the wavelength is shorter, but the height is about the same. So these two waves, when you're comparing, the second one has a shorter wavelength and same amplitude. This one, you see, like the peak to peak distance is about the same as the original. So I'm talking about peak to peak distance, right? So peak to peak distance is about same as the first one. So I would say same wavelength, but the height is smaller on this one. So this has a smaller amplitude. Likewise, on this one, it does have a shorter wavelength and also the shorter height. So it is a smaller amplitude. Then frequency is a very interesting factor. That is what we are hearing. So we are very familiar with this one. Even though I use the word frequency, it's same as the pitch. So frequency is measured in hertz, and that is the number of waves which passes a given point in 1 second. So if you're measuring how many waves are passing in one particular point in 1 second, and if you count how many waves are going, that's the frequency, right? So here, If you count how many waves are passing one point in 1 second, here we would have seen a higher number of waves that passes in 1 second than the second wave over here. So this one has a high pitch and this one has a low pitch. Then there are two types of waves, transverse and longitudinal waves. So let's look at what is a transverse wave is. So transverse wave have oscillations that are perpendicular to the direction of the wave travels. So here we can demonstrate these waves using a slinky. So imagine that there's a slinky, and if you move it like up and down, then there's a wave that propagates along the slinky, but the materials or the particles in the slinky will move up and down. But you will be observing a wave that propagates horizontally. So these are transverse waves. So examples of transverse waves are the waves that's created on a rope. Then electromagnetic waves are also transverse waves. We'll learn about electromagnetic waves in a few minutes. And some seismic waves are also transverse waves. So here we can observe the transverse waves and longitudinal waves. So in a transverse wave, so the top one is the transverse wave, the second one is the longitudinal wave. As you see here on the first diagram, the transverse waves are propagating. So you see the wave propagates this way, but the slinky is not, right? Slinky is moving up and down. Then in the second one, the wave propagates horizontally, the materials are moving back and forth horizontally. Right, so the longitudinal waves have oscillations that are along the direction to the wave travels. And here the examples include, let me get rid of the full screen here so I can remove this video, and I'll show you what is a longitudinal waves looks like when you're drawing in a picture. So here the wave is propagating horizontally, and the molecules or the particles in the slinky moves back and forth like in this picture. So those are longitudinal waves. So sound waves and some seismic waves are longitudinal waves. So importantly, sound waves are longitudinal waves. So in order to hear sound, there should be a medium around us. So there should be some pulse going into our eardrum, right? So if you are in a space, like an empty space, then you should not be able to hear the sound if there's no materials in there, like a vacuum space. So you may think about, can astronomers hear each other in space if there's no atmosphere there? So there's no air, so can astronomers hear each other? All right, so one important fact about waves is they do not carry matter, but it does carry energy. So if you think about a wave in a whip, the whip does not move, but will you stand up in the back of the whip? I mean, the end of the whip? We don't, right? So it's bringing a big energy along the rope to the end of the rope, right? So energy is propagating in these waves. Then let's define the waves. So wave is a traveling disturbance that transmits energy with no net movement of matter. So the disturbance is frequently called an oscillation or a vibration. The substance through which the wave travels is called the medium. Now, let's look at light. So, you know, like light behave like a wave in one point, and sometimes it's behave like a particle. So here, in one of the Newton's experiments, he demonstrated that white light is a mixture of colors. So as in this example, if you're using a prism, and when you send the white light through that, it can create a rainbow colors. Then using a second prism, you can collect these rainbow colors back again to white light. So we can conclude that the white light consists of 7 colors. Then the light is an electromagnetic wave And there are other electromagnetic waves as well. So let's understand what is an electromagnetic wave. So here, electro and magnetic. So there's a electric field oscillation and a magnetic field oscillation. I think I mentioned that electromagnetic wave is a transverse wave. So the wave should propagate perpendicular to the motion of molecules. So here there's no motion of molecule, there's no slinky, but the fields are oscillating. So in an electromagnetic wave, we can see the electric field oscillation is perpendicular to the wave. So here in this picture, the wave is propagating along this line, and the electric fields, which are represented in red color arrows. So as you see, the electric field oscillates up and down, up and down, up and down, right? So the electric field oscillates perpendicular to the wave propagation, and the magnetic field, which is denoted in blue color arrows, it oscillates perpendicular to the electric field and also to the wave propagation. So these three things are perpendicular to each other. Three things means wave propagation direction, electric field vibration direction, and the magnetic field vibration directions are perpendicular to each other. Then again, it is a electromagnetic waves, but still you can measure the wavelength, right? So the wavelength is peak to peak length. So if you measure the distance from this peak to that peak, that's the wavelength. That's the direction of wave propagation. So the electromagnetic waves are propagating incredibly large velocities. So the speed of light is 300,000 kilometers per second. So if you look at it in miles per hour, it is a huge number. So let's look at it. 671 million, 80,888 million miles, sorry, 671,080,888 miles per hour. So it's a huge speed, right? So we cannot imagine like we are traveling in that speed. So there are so many ideas within the scientific world that if we can exceed this speed, we should be able to travel in time, right? Anyway, those are concepts only yet, but you may think about those when you're creating your curious questions. All right, so in addition, they can be produced with an extremely wide range of wavelength. You know, like wavelength can be varying, right? So in the electromagnetic spectrum, the visible light is just a small range, but there are other waves that we cannot observe with our eye or our ear that is included in electromagnetic spectrum. So using telescopes, we should be able to catch some other electromagnetic waves than the visible light. It is really important, and from there we can obtain a lot of details. Well, so in the electromagnetic spectrum, we can see the a huge range of wavelengths. So in this one, the bottom line is represent the wavelength. So you can start from 10 to the power 5 and go all the way up to 10 to the minus 16. I should say it in the other way around, right? So it start from 10 to the power minus 16 and go all the way up to 10 to the power 5. Within this range, we can see the radio waves, which has the largest wavelength. Then like FM and AM radio waves. Wi-Fi belongs somewhere here, and then there come the microwaves. So in the microwave that you use to warm your coffee or the milk, we are using the waves in this range, so you can't see it, but it is very similar to the visible light. Only thing we cannot observe it. Then the IR spectrum, then comes the visible range. See, like it is a very narrow range, right? Then the UV light, X-rays, and gamma rays. So gamma rays has the smallest wavelength, but high frequency. High frequency means it has high energy. Now, if you look at the visible light, we are very interested in visible light because that is what we can see, right? So in the visible light, the red light and the blue light lie in the end of the spectrum. So red light wavelength is about 700 nanometers. Blue light wavelength is 400 nanometers. And as I mentioned, high wavelength means low frequency. Low wavelength means high frequency. And high frequency does have high energy. So blue light contain high energy than the red light. So we feel like red is dangerous, but blue is the dangerous one. All right, so if you compare the wavelength of these electromagnetic waves, so the wavelength of radio wave is about more than the size of a building. Then the microwave is 10 to the power -2 meters. So it's about a size of a human. Infrared is the size of a honeybee, I would say, 10 to the power -5. Then the visible light is in the range of protozoans and pinpoints, like in between this. And then molecule size is the ultraviolet light. X-rays are about the size of an atom, and the gamma rays are about the size of an atomic nuclei. So you can imagine like how small they are, right? So we are not able to see these. Then the frequencies, as I mentioned, for the gamma rays, frequency is higher than the radio waves. So radio waves have 10 to the power 4 frequency or above, below, and atomic nuclei size or the gamma ray frequency is 10 to the power 20. So they're moving really crazily, right? So it's high frequency and high energy included in that. So these waves, the electromagnetic waves, can travel really a high speed, as I mentioned. So let's think about speed of light. So speed of light is 299,792,468 meters per second. For easiness, we can write it in scientific notation, which is 3 times 10 to the power 8 meters per second. We are not familiar with meters per second, so let's think about miles per second. Miles per second, it's going to be 186,000. Still, miles per second is not make sense, right? So let's look at the numbers in miles per hour. So miles per hour, it is 670,616,651 miles per second. Miles per hour, right? So it is a huge number. So we cannot imagine like traveling in that speed using our vehicles. So this is a large number. Is it make sense? We don't know, right? But the Maxwell predicted this number earlier, and then Olaf Ramo had measured or the noticed there's a little delay in the apparent orbit Jupiter moon and calculate the speed of light to be close to this number. Okay, so he uses the motion of Jupiter and the moon and then calculate the speed of light, and he found it closer to this number. So experimentally, it has been proved. So let's get familiar with this speed of light a little bit. So as I mentioned, light propagates at a speed of about 3 times 10 to the power 8 meters per second. And we know like speed is distance divided by time, right? So we say miles per second. So basically we are looking at the distance it traveled in a second, right? So basically you can calculate the speed using space or the distance divided by time. So in this case, we can calculate the distance that light travels in 1 second. So the speed is 3 times 10 to the power 8 meters per second, and it travels 1 second. So we end up getting 3 times 10 to the power 8 meters. So in a second, it can travel 3 times 10 to the power 8 meters, or in miles, it can travel 186,000 miles in a second. So in 1 year, light will travel a distance is called the light year. So in a second, it can travel 186,000 miles, right? So using this number, we can calculate like how much distance it travels in a year, right? So so we say we think that it's 186,000 miles. It takes 100. So in a year, light can travel 186,000 miles. Okay, so in 1 light year is about 63,000 astronomical units. So in 1 year, light can travel 63,000 astronomical units. So it is a huge distance, right? So that's a good fact about this idea. So imagine Proxima Centauri, that is the closest star to our sun. So it is about 4 light years away from us. So this means that light emitted from the star will take about 4 years to reach to Earth. So now you're seeing a star that is 4 years older. So you're basically looking at an old picture of the sky, right? So the light traveling is giving us an idea about the age of the universe. So astronomers like distance object because they give a snapshot on the early stage of the universe. Another example is a quasar called SDSSJ084119.52. So we are not going to read this number, only that is the name of this quasar. So it has been reported to be 12.7 billion light years away from us. So we are seeing this light that's emitted by this quasar 12.7 billion light years ago. So maybe that quasar is there, maybe not, because it's a long time ago, right? So we are seeing the old picture of the universe here. Then there are absorption spectrums. So when you go to the atomic level, it can absorb the electrons in the shells, can absorb energies, and they can jump into the upper energy level. So you'll be seeing some energies are missing. So that's due to the absorption. Then also we can see emission spectrum. So when we with the atoms, when the atoms are excited, they can emit the energy out. So the electrons in the upper levels can jump back into the lower levels. So in that case, it will be emitting light. So this is called the emission spectrum. So you see like there's a emitted light in there. So in a continuous spectrum, you can see all the 7 colors, but in the emission spectrum, you will be seeing only few colors. And in the absorption line, you will be seeing missing colors because the energy was absorbed. So in a hydrogen, this is the color spectrum. So if you see this emission spectrum, then we can recognize hydrogen. Then helium has its unique spectrum, and mercury, not the planet Mercury, the element Mercury, this is the spectrum. So each element has its own spectrum. So by analyzing the spectrums, we can study these elements. All right, so maybe you have seen colorful fireworks, right? So how do that color comes from? From where those colors come from, right? So here, the red color coming from the strontium salt. So they're using strontium salt in the crackers. So that's why you see the red color. Then orange color comes from calcium salts. And the yellow comes from the sodium salt. And the green comes from the barium salts. Then the blue color, copper salts. Then the purple, combined copper and the strontium compounds. And the silver is coming from the white hot magnesium and aluminium. Then the white color comes from the burning metal. So it could be magnesium burning, aluminium burning, or titanium burning. Right, so these colors are produced by the chemicals that they're using in the crackers, and these are the emission spectrum. So each element does have their own emission spectrums. Okay, so why is the sky blue? I think we learned about this one earlier. So the white lights coming from the sun is actually a mixture of light of different wavelength. Then the shorter wavelengths like blue light are scattered by gases, molecules in the atmosphere more than the shorter wavelengths such as red. So the blue light enters our eyes after being scattered multiple times, and it's appear to come from all part of the sky. So we see this blue sky in the daytime. Then the sunrise and sunset, we'll be seeing the sky in different colors like red and yellow. So in the sun setting and sun rising, the sun is in the horizon. So the light travels a longer distance than it's on overhead to us. So the blue light will scatter vigorously and loses its energy, but the red light are not that energetic, so they're coming slowly and survive for a long time. So we can see the sky in red color. All right, so thank you, and I'll meet you in the next video about image formation and applications. Then after that, we will learn about telescopes.